Hello and welcome to this lecture which continues the Scilab presentation. We told in the earlier lecture that Scilab is a very powerful software which can do all your numerical computations very effectively, and this Scilab is being used on an international level for many important projects. So, it is a very effective software and it costs nothing. So, we should always in academic communities, we should always go for those softwares which are freely available, so that we have to save on our expenses. So, last time we considered several elementary operations which can be done on Scilab. Of special interest was this definition of a function. In a Scilab, we can also define a function. So, I want to define a function func of x. The first line is function value equal to function of x. So, there is the first line, and the second line gives meaning to that value equal to exp into bracket x plus exp into bracket minus x comma end function and double slash. Double slash is only as whatever follows after the double slash is a comment card. Now, we notice that in the function from the beginning function up to the end function, there are many statements and they are separated by commas, not semicolons. Okay. So, this is how I define a function, and once I define a function, I can calculate the value of that function at any value of x. X could be any value. This is how I will calculate function in the rest of the Scilab operation. After this, we also considered how to use trapezoidal rule. I discussed it in the last time. I will not repeat this part again. So, you can define a variable t in the range between 0 and 1 in a spacing of 0.01. So, this is like a do loop. So, I define all the values of t, 101 values through the single line. Then using trapezoidal rule, I obtain an integral of exponential of t. T is already given at 101 points, exp t is calculated at 101 points, t has 101 point, and this whole function gives me the integration using trapezoidal rule. So, the same thing can be done using a program, and I have also discussed it in the last class. So, what I want to do today, this integration also we discussed. In particular, I want to integrate now some function, say sin x. So, I want to integrate this function sin x from x, starting value is x, okay. Function is x, function is sin x, variable is x, starting value is x0, x0 is the starting value which I have given as 0, and x1 is an array, x1 is an array consisting of 0 to pi spacing of 0.1. So, there are many points here from 0 to pi, in fact, there will be 31 points, and I will be integrating sin x from the starting value of x naught to each one of these 31 points. So, I will have the integral for those 31 values of the upper limit of integration. Lower limit is x naught, upper limit is this x1. So, you execute it and you will see that you will be able to integrate this function sin x in this range. So, in place of sin x, I could have any other function. Suppose I have a very complicated function which is defined through the function as I have discussed earlier. So, I can define any complicated function, then I have a variable x and I integrate that function between the starting point and ending point. So, this is a very powerful way to integrate functions for which we do not know the analytical values of the integral. So, this is how I do integration, and since I can do the integration, then I can also solve differential equations. How will I solve differential equations? So, this is a method to solve differential equations using Scilab. So, I have this differential equation dy by dt. Okay. Let this equation be dy by dt equal to y square minus y sin t plus cos t. Okay. So, this is my differential equation, y 0 equal to 0 is the initial condition. So, I want to solve this differential equation. Okay. So, what are the commands for that solution? One would be I again now define that y dot. Y dot is my function. function y dot equal to f of t comma y. So, this is my function. Then y dot equal to y square minus y sin t plus cos t. So, this is my value of y dot end function. So, this defines the function and now I want to solve the differential equation. So, what is the command to solve the differential equation? So, command is ODE. ODE is the command for differential equation. Okay. And what are the variables that go into that ODE? ODE will require y 0, t 0, t and f. Okay. So, y 0 is my initial value of y, t 0 is the starting value of t. Okay. And what are the values of t now? T will take on values from 0.1 up to value of pi. So, this particular line t equal to 0 colon 0.1 colon percentage pi means it is the values of pi in radians. So, this t is a variable that takes values from 0 to 3.1415 in increments of 0.1. So, these are the values of t. So, I want to solve the differential equation so that I have the solution y for all these values of t. Okay. So, that is my solution. So, y equal to ODE y 0 t 0 t f, f is the same function I defined earlier. So, you will see that this is almost like a subroutine. Remember in Fortran we used to call subroutine. When I call a subroutine, it takes the values of whatever variables there are and gives me the solution to the main program. So, you assume that your Scilab is like a main program that is running and all these functions and routines give you ways of calculating solutions to these equations. So, this is to solve an ordinary differential equation. Now, after you solve, you can also plot using Scilab. One of the most important advantages of Scilab is that whenever you solve a problem, you can plot it and see y as a function of x or y as a function of t. So, we will demonstrate it as we execute all these programs in Scilab. So, this is our solution of a differential equation. So, next we will when you give this command y equal to ODE y 0 x 0 x f, it gives the answer of y in the form of columns. So, what are these columns? These are all the solutions of y for different values of x. Okay. So, 1 to 12, these are the solutions, column 1 to 12, then they will have all up to full, all the columns will be there. Okay. So, now I have given only between 1 and 12, others you will see when you execute yourself. So, after doing all this, the next thing I want to do a little bit is what is called Scilab programming. Remember in Fortran, we know how to do programs in Fortran because there is a structure to that language. Everything you want to do mathematically, there is an equivalent programming language to do that operation. So, in Fortran in particular, the do loop was do 10 I going from 1 to 10, then all the statements all the statements in the do loop will be executed until this I takes the last value of that index variable for the do loop. Now, for example, here I have given x going from 1 colon 20. So, that means x will take these 20 values. Okay. So, that is this almost like a it should have been x. Okay, let us go to the next one. I think there is something not correct in this. So, there should be x colon 1 colon 20, in which case it will take x from 1 to 20 with a spacing of 1. So, this may also take on 1 to 20 in increments of 1. This could be the default value. Now, this is how I will do a do loop in a Scilab program. How do I do this do loop? For I going from 1 to 10. So, this is my do loop statement, comma yi is equal to xi plus 2 colon semicolon end. So, this is the do loop. In an earlier statement, I have already defined x 1 to 20. There will be 20. X will go from 1 to 20. So, in my second loop, I goes from 1 to 10 and yi goes from xi plus 2. Each yi is xi plus 2. Now, you see that this x was going from 1 to 20. So, I calculate y for those values 1 to 10 and this is listing all the values. Okay. I have listed a few values here, first 4 values. So, this is how I will estimate a do loop, and what I have done here y and I enter. So, when I enter y, it will give all the 10 values of y, because y was only taking 10 values. Okay. So, this is how I will execute and give the output for y. So, this is how I will do some elementary programming in Scilab. Okay. So, now a very interesting thing, how will I plot using Scilab? So, there are many options to plot in Scilab. In fact, it is extremely powerful. So, there are different kinds of plots. There is a 2-dimensional plot, there is a 3-dimensional plot. So, you can practice with several types of plots. Okay. So, let us take the simplest example. Normally, we need these 2D plots. What does a 2D plot do? You have a variable x along the x axis, you have a variable y along the y axis. So, the plotting command is very straightforward, plot into bracket x comma y, it will give you a 2-dimensional plot. Okay. So, example of this plot is given in the next slide. So, this is this plot. In fact, what this plot does, it is the solution to that ordinary differential equation. Remember, we solved an ODE. Once you solve an ODE, you can just plot the result in this manner. You can just plot the result. Okay. And once you plot, you also need to give labels to the x axis and y axis. So, there is a procedure for that. X title is equal to ODE. So, this is the title I want to give on the x axis. This is the title I want to give on the y axis. Okay. So, and once you plot this graph, you can also save this graph into your directory by giving this command access to JPG into bracket 0 comma ODE. So, I can save these on my hard disk using this command, access command. So, this is how you will plot and save. Now, the next thing I want to do, remember in chemistry, we study a lot of orbitals, and the radial part of the orbital is given by a certain set of polynomials, and the angular plots are given by another sets of polynomials. Those angular plots are called Legendre polynomials, and the Legendre polynomials p and x. Okay. So, n is the index. So, I have first p 0 x is a constant function, p 1 x is just x, p 2 x is half of 3 x square minus 1, p 3 x is 1 by 2 into 5 x cube minus 3 x. These are nothing but these are your shapes of orbitals. This is your p orbital, this is your d orbital, this is your f orbital. So, similarly, there are many functions now. So, what I want to do, I want to calculate all these Legendre polynomials and plot the entire set, So, that is what the next slide. So, this is an example of a third polynomial. So, let us say I just want to plot the third polynomial. Here the visibility is not so good. Okay. So, I want to plot the value of x takes on the values minus 1 colon 0.01 colon 1. So, that is the values of x are from minus 1 to 1 with a spacing of 0.01. So, this is my do loop. So, this will generate 201 values of x, and once you generate 201 values of x, now you want to generate all the values of y. So, what are the values of y now? Go back to the slide. Values of y are half of 3 x square minus 1. So, this is my function. So, that is what this is doing, yi equal to, this is not 3 x square minus 1, this is 5 x cubed minus 3 x. So, what it does? It calculates for those 201 values of x, yi is equal to 5 into x cubed minus 3 into x whole thing inside a bracket divided by 2 colon semicolon end. So, this is a do loop now. This is a do loop which executes for 201 values of x and calculate the function yi. Now, when I say plot x y, this will give you the plot as shown below. So, this is the plot of that third Legendre polynomial. This is how it will look like. Now, once you plot one graph, our interest would be, can I plot several graphs on the same sheet? Because many times when you have lots of calculations, you want to plot more than one graph on the same paper or on the same setting. So, that is what is shown in the next slide, but before I come to that, I will also tell you about another command which is called an editor command. Now, the use of this editor command, suppose you have a large number of statements which you want to execute and you want to save it in a file and then execute all of them together. Say for example, you may want to invert a matrix, you may want to calculate some functions, you may want to do many things and you want to save it in one file and execute. This is like your program in Fortran. So, in a program you may want to do interpolation, you may want to do fitting, then you may want to do integration. So, all those commands you want to put in one file. So, to do that I can use a command called editor. So, the moment you type editor on a Scilab screen, a new window will appear. A new window will appear where you can write all the commands that you are going to execute later. So, this is like now a program inside a Scilab. Okay. So, write all those commands using your editor and save it. Okay. And you save it, when you save an editor, it will save it with an SCE extension. Okay. It will save it with an SCE extension, and when you want to execute that particular file, just type execute file name dot SCE. So, this is how you will execute all the lines that are saved using an editor command. So, this is an executable file. So, you can execute using a file name dot SCE. Okay. So, what I will do now, I will create using an editor a set of lines. So, that is shown in the next slide. So, look at this slide now. What this slide is showing, I am going to create a large number of Legendre polynomials and I want to plot all of them at the same time. So, how do I create this? As I did earlier, my x is a variable. That variable goes from -1 colon 0.01 colon 1 semicolon. So, that means now this is like a do loop. It takes all the values of x between -1 up to +1 with a spacing of 0.01. So, there will be 201 values of x. Now, to determine all the Legendre polynomials, okay, to determine all the Legendre polynomials, I have a separate loop for each of the polynomial. For example, the first Legendre polynomial was a constant. So, I execute this loop I going from 1 colon 201 yi is equal to 1 end. What was my second polynomial? Second polynomial is nothing but the value of x. So, for I going from 1 colon 201 comma y2 is equal to xi semicolon end. So, this is my second function. So, similarly y3, this is my third function. Okay. So, there is some error here, this should have been y4, this should have been y4, this should have been y5, this is y6, y7, y8, y9, y10. So, there are these errors, but of course, you can correct them because you know that this is the first function which is constant, second function is x, third function is x square minus 1 divided by 2, fourth function is xi cubed minus 3 xi by 2, this is my fifth function 6, 7, 8, 9, 10. So, once I generate these functions, now all these functions have been generated for 201 values of the independent variable x. Now, I want to plot all of them. Okay. I want to plot all of them. So, the command is given in this particular line. So, I want to plot these 10 Legendre polynomials. Okay. So, but when I type all these things, I save it. Remember, I create it using an editor command. I save it as a legendre.sce. Now, I will execute that entire file. So, when I execute the file, it will generate me all the polynomials. Now, I want to plot all of them. And you know that the plot commands, if I wanted to just plot y1, I will say plot 2d into bracket x comma y1 bracket complete. but since I have 10 of them, so I will plot it like this, plot 2D into bracket x comma, this is a round bracket, this is a square bracket, x comma, in the square bracket y1, y2, y3, y4 all the way up to y10, square bracket complete, the round bracket complete, semicolon. So, this will plot all the functions. So, let us see whether I have this, I do not have it, we will execute it. We will execute it in reality when we do the demonstration part of the Scilab. So, this is plotting function. Now, there is another important function I want to spend time on, it is called the fitting function. Remember when we did programming, we fitted a polynomial to a set of data points. Okay. So, we also fitted a straight line. So, Scilab also gives a procedure to fit function to a given set of data. This is a slightly more involved set of statements than the ones so far, because so far you saw that everything was either a one line statement or a two line statement. Now, this fitting function is little more involved. So, I shall illustrate all the statement first and then we will execute it in Scilab. Okay. So, now curve fitting using Scilab, okay. I shall use it first for an exponential fit, then I shall demonstrate it for a linear fit. Okay. So, for curve fitting, what is my starting point? My starting point is x and y, x is my independent variable and y is the dependent variable, this is the data that is given. So, before I start my Scilab program, I need all the data points. So, I take some simple set of data. So, what is my data now for this exponential fit? X is an independent variable, it goes from 0.1 starting value colon 0.2, this is the spacing colon 2.1. Okay. So, starting point is 0.1, last value is 2.1, spacing is 0.2. Okay. So, you will have as many values, okay, 0.1, 0.3, 0.5. So, the last value will be 2.1. For these independent values of x, I have dependent values now. What are my dependent values? 0.9, 0.75, 0.6, how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 values of the dependent variable y, I have 11 values of the independent variable x, and now this is my fitting program. So, these are all the lines, you just look at the lines first and then execute it. So, how do I execute? After I define x and y, my next line is function y is equal to xx, function y is equal to ff into bracket x comma p. So, this is a definition of my function, ff into bracket x comma p, comma y is equal to exponential of minus p star x, because I want to fit my function as an exponential function. So, it is minus p times x end function. So, the next line was definition of this function y. Okay. So, then we need some more statements, then next statement should be z is equal to in square brackets y colon x square bracket complete semicolon. Okay. So, now there is a criterion function. So, what this does, this particular fitting function calculates a criterion function E and it does several operations and giving me the final result. Function E is equal to into bracket E is equal to G into bracket P comma Z bracket complete comma, then Y is equal to Z1, X is equal to Z2 semicolon, E is equal to Y minus FFXP. So, Y was my original data, FFXP is the calculated fitted data. So, what the program does, it will keep on iterating until this E, which is an error, is reduced to a minimum. Okay. So, the whole trick in fitting is you calculate the fitted function, compare with the data, if the error is too much, then I reduce the error, keep on iterating. So, this particular set of lines does all that and finally, it will give you a fitted function. Okay. So, after this set, so to solve the problem now, I need to give a value of P0 and P1. So, P had two values, P0 is 0.8 okay, and P colon ERR in square bracket is equal to data fit G comma Z comma P0. So, this is the function, this is a next function, then SCF is equal to 0, it will clear the screen, then plot 2D x comma y comma minus 1. So, this is plotting the data. Okay. Now, next is x y comma minus 1 plots you the data, and plot 2D x comma ff x comma p comma 12, it plots the fitting function. So, the first one plot D is to plot x and y, and the second one is to plot your x and the fitted function, and the third line in that plot function tells you what kind of plot you have. Suppose you want stars for your data points, you will give some number, you want some other symbols. So, the third line, the third variable in the plot gives you how I should identify the data. So, we will execute it shortly. Okay. So, now since I have done this execution. Okay. So, some more things here. So, Z, remember, so just execute it. I think the best thing is to execute it and get a feel for it. It is a little involved function. So, this is just the more details on what your fitting function is going to do. Okay. So, this tells you little more of the nature of x and y and the nature of this z. Okay. This is how the z will look like. So, this is how your criterion function works like. Okay. Okay. So, now if I want to extend the same thing to a linear fit. So, I have done a exponential fit. Now, how will I do it for a linear fit? Just see this, this is a little easier. X is equal to 0.1 colon 0.02 colon 2.1. So, this is my value of x, this is a set of data points. Now, I want to fit a linear function. When I fit a linear function, what do I do? That y of ff into bracket x comma p, this y function now is p1 x plus p2. This is a linear function. In the past, it was a exponential function. So, end function, then z is the same, y colon x, criterion function, e is equal to g p comma z, y is equal to z1, x is equal to z2, e is equal to y minus ff x p, end function. How do I solve the problem? Okay. P0, I want to give an initial value of P0. See, remember, this P is having two values, P1 and P2. This is my initial values of P. Then I define this P error, clear the screen and plot not only y, but also fitted function y. Okay. So, what I will do, I will conclude this lecture here. I have two more rather very simple statements. I will explain these and then we will execute the Scilab in the next lecture. So, I will close here. Look at all these comments, look at all these slides, so that you will be familiar with all the commands that you need to use in Scilab. I will conclude here. Thank you.